or are taking physics?
Oh, yeah.
Physics, anyone? Physics? All right.
Work.
How? Hey, I asked you a simple question to raise your hand. No talking required.
No. Just like, if I'm not going to pass it,
What?
why not just
Be quiet. Do I already have my notes? My work notes. What do we know about work? What did you say, Lillian?
Force times displacement.
Force times displacement. So, if I were to pick up Gabe, and lift him 2 feet off the ground, okay, I would take 150 pounds times 2 feet, and I would be doing 300 foot-pounds worth of work. Are we
And
okay
then
with
you
that?
can convert it to joules.
Okay.
You convert it to
Now, I know those of you who are like really into physics, you're going to be annoyed with the whole foot times pounds thing.
Oh,
But,
Newton.
yeah,
So
but
that
that's
is kind of bugging me.
you're going to have to get used to it.
Oh, my
Okay?
goodness.
But joules
Now,
is-
what is going to be the issue, or why we need calculus, is not always will we have a constant force.
Oh,
Okay.
yeah.
For example, maybe
We have it.
I have a chain that I'm lifting up from the ground. Well, as I lift in my chain, what's happening to it? It weighs less, and it weighs less, and it weighs less, right? Because it's shorter, okay?
Yeah.
Or maybe I'm picking up a bucket and it has a hole in it, and so water is leaking out. So as I raise the bucket, I don't have a constant force because it's weighing a different amount at each
How
time.
much? How
Okay?
much stone is under the bucket?
So we're gonna do a leaky bucket problem. Don't you worry.
How tall is the
I
cone
wasn't
under the
worrying,
bucket?
but now I am.
You need
Okay.
calculators out today?
Yeah.
I hope we don't.
So we're gonna need to actually integrate our force times displacement. Okay? Which is where that dx comes in. Okay? Because it is changing as we go. Right? So the things that you could do in physics, we've now like opened up this whole new door of possibilities. And I hope you're excited. Okay? One thing that you have done is Hooke's law.
Is it the spring one?
That is the spring one.
The
Okay.
spring force?
Now, the way that you've done it, you actually didn't know the calculus behind it. Mr. Marsh teaches it to you, and but doesn't put in this piece of integration because not everybody knows integration. Okay, so we're gonna go over Hooke's law, and it's gonna be like way better because we can use an integral instead of like memorizing a formula. All
Does
right.
that just say the integrals of x dx?
Yep.
Okay.
Okay.
So it's not going to be that complex.
Nope. Well. No. All right. So Hooke's law of springs: the amount of force it takes to stretch a spring is proportional to the length that is already stretched. Okay. So those of you who have taken physics, which it sounds like everybody, raise your hand if you've done Hooke's law for springs. Just not you. Okay.
I mean, I'm in physics right now.
Okay. So you'll get there. You'll get there.
How about you?
We have to figure out what that spring constant is, and then what we can do is we can throw it in an integral because as we stretch a spring, the force is going to vary, right? The more we stretch, the more force we have to use. Would you agree? Like stretching it from here to here versus here to here, you're going to have to use more force to do the same amount of work. Okay. So I'll go through one of our spring problems. Okay. And then we'll get into non-spring problems. I was thinking the same thing, but I held my tongue. Glad we're on the same page, Jackson. Are you ready for some springs? Now, annoyingly, we are going to be in foot pounds. And I'm very sorry. Okay?
Why is that annoying?
So in physics, you guys work with like the metric system, right? In math class, we don't. I don't know why. I don't know why. Okay? But your book is written in feet, and in pounds, and so I want to do examples that match that. Okay? So a 2-pound weight. 2-pound weight stretches a spring from its resting length of 1 foot to 1.5 feet. Find the work it takes to stretch the spring from 1 foot to 1 foot 9 inches. Okay. I'll let you write down what you need.
That's how you eat that respectfully.
Oh,
Okay, we just stared at me.
And Micro, every single day without fail, hold like sits right next to me, pulls his apple right out after lunch.
It's not
He just makes that
it's
apple
not just the
crunching
stats,
noise.
it's chemistry and it is the
Okay, are we ready? Do you have written down what you need?
Yes.
Who needs more time? So, we know that the force is directly proportional. Blah, 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 blah. So, our force is how many pounds? 2. And we stretch the spring how far? Half of a foot. So, our spring constant is 4. He asks with a question mark.
No question.
That was a statement.
So, for our work, to stretch the spring from its resting to a foot 9 inches, a foot 9 inches, we would integrate. Resting would be 0. How far are we stretching it? Okay, well, are we going to put 9? Okay, we're going to want to put 3/4 or 0.75 if that's how you want to roll. Okay, and then our force, which is 4x. Okay, so you know all of your work that you did with 1/2 kx? Where does that come from?
The integral. Wow.
Or 1/2 k, excuse me, 1/2 k.
Life is just the integral.
Yeah. 1/2 kx squared. Sorry, I was panicking, but yeah, that's the integral. Okay, Joe.
So if it's wait, so when x is 1, wouldn't f equal 0 then? No wait, because x would also be 0 because the displacement is 0.
Okay, you answered your own question. All right, so we integrate 1/2 kx squared. Okay, now we know where it comes from. We evaluate from 0 to 3/4, so we throw 3/4 in there and we get 9/8 foot times pounds.
Oh.
I'm sorry. Now, what if I asked you, find the work to stretch it 3 inches farther?
Well, then you just said
Then I want you to talk to your neighbors about what the limits of integration would be. Stretch the spring now an additional 3 inches. Talk. Okay? If we're going to stretch it 3 inches farther, Hannah, what would our limits of integration be? 3/4 to 1. Give me, Darby, a reason why she's writing 3/4 to 1.
Because you're already at
Okay, we've already stretched it 3/4 of a foot, so that's where we're beginning, and then we're stretching it to where we're a foot past its original length. Okay, does that make sense? Okay. Yes.
Because if you just plug in one into the equation, then you the total length you need to stretch it 1 foot, but you need to subtract it for what it took to get to 1 foot.
What are you talking about, one?
The limits of integration doesn't start at 0 because if you want to stretch it 3 inches farther,
Oh.
then you find the work that it took to do that, and you have to
Yes.
subtract the previous.
I'm understanding you. I'm understanding you. Yes, you are correct. You are correct. All right. A very popular problem, lifting a chain. Okay, I already kind of gave this, was kind of like my example of how we couldn't use the force times displacement every single time because our force could be varying. Like in this example where I am lifting up a chain. Okay, so a 40-foot long chain that weighs 80 pounds is dangling from the top of a cliff, and I want to haul the chain up to the top of a cliff. Do you think this is something that has happened before?
100%.
Okay.
I mean, a rope as well.
Yes. Yes. So you could. And would it make sense that we know the length of the chain and the total weight of the chain? That sounds reasonable. An 80-pound chain, though. Ugh. It's a heavy chain. But I suppose chains that are sturdy would be pretty heavy.
You're probably lifting something.
Do you even lift an 80-pound chain?
So much does that
That would proportionally be about 2 pounds per foot. Chain. I mean, a 1 foot of chain is 2 pounds.
All right.
They all lift.
So let's talk about the weight.
Oh, I think.
Let's talk about the weight of our chain. Yes, I know that our chain weighs 80 pounds. And I know that our chain is 40 feet long. But if I am pulling it up, I don't care that it's 80 pounds. I care that
How
it's what?
much is left to lift? 80 pounds per foot.
Exactly. I know that there's 80 pounds for 40 feet. So we would have 2 pounds per foot. Why is that important to know? Because based on how much chain is left, we can figure out how much it weighs. Okay. All right. So our force is varying because our weight varies from how much we're lifting it up. Okay? So our work that we're going to calculate, let's think about our force. Okay? Our force is going to be 2 pounds times however much is left. Okay? So I'm going to say that is change in y. Depends on how much is left. Okay? Since we have a cliff and we're dangling off, okay, this chain is 40 feet. Now, how could I calculate the displacement at any given moment? The displacement is going to change, but how could I calculate it at any given moment? How could I describe it? 40 minus y. So what we're going to set up is we're going to set up the integral 2 times 40 minus y, that's a y, dy. Okay. 2 dy is essentially our force times displacement 40 minus y. Are we okay with why we are choosing 40 minus y? Okay. If 40 minus y is how we're describing our displacement, what would our limits of integration be?
0 to 40.
0 to 40. Okay, because we're going to do the whole chain.
So the displacement is the dy.
Well, I would describe the displacement as like 40 minus y. Because when we're at,
Oh, right. Okay.
okay, the force I would describe as 2 dy.
Okay.
Because it's 2 pounds per foot, and then the dy, it,
Yes.
like we have to sum up where it is. Yes.
If the weight is decreasing,
Mm-hmm.
wouldn't it be good
No. 2 is how many pounds per foot our chain weighs. So if 40 feet is dangling off, it's 80 pounds that we are lifting at that particular moment in time. If we've gotten half of it in, and there's 20 feet left, 20 times 2, there's 40 pounds of weight hanging off the ledge. If there's only 2 feet dangling, we have 4 feet of chain. Are you with me? You were.
I was still struggling. There we go.
All right. So we could do this without a calculator, but let's just save some time. Oh, Joe already did it without a calculator.
1,600 foot. Because you get the line
Sounds good to me. Okay. Why are we having to integrate? Because our force is varying. Our force at any given moment is different. Okay? When I lifted up Gabe, his force stayed the same. He didn't lose any weight in the 2 seconds that it took me to lift him. Okay.
Oh no, the leak.
The leaky bucket.
What is the height of the cone? Are we gonna have to define the height of the cone and how much force?
Read it. We have a leaky bucket.
But sometimes it comes from the price.
Okay. So a leaky bucket that is 5 pounds is raised 20 feet. The rope weighs, I even tell you, 0.08 pounds per foot. The bucket starts with 2 gallons, 16 pounds, of water and is empty just in time to reach the top. What is the amount of work used to raise this up? First question, excuse me, how many different forces do we need to consider?
7.
We have the bucket, the rope, and the water. Okay? I disagree that the rope doesn't change.
Oh.
Kind of like our chain.
Well, the
But
rope
good
and the wa-
news, does the bucket change?
The rope and the water change the same rate.
Mm,
The water,
I don't know if I would say same rate.
well, as the water decreases, the rope will also take less force.
So let's start with our easy one, the bucket. Would you agree that our bucket has a constant force? It's 5 pounds. And how much do we lift it up? So 5 pounds times 20 feet, we're talking 100 foot-pounds.
So that's not going to go in the integral.
No,
We're not doing an integral of that. That's gonna go.
we'll add it in later. Also, when we think about the water and the rope, we're going to think about two different integrals. Okay? We're going to find the force of the water separately from finding the force of the rope. Okay? Because they're separate entities. Okay? All right. Rope or water?
Rope.
Oh, this is just a chain. The rope is just a chain.
The rope is going to be very similar to the chain, right? We're talking about 0.08 pounds per foot, and we're talking about lifting it up 20 feet. All right, so very similarly to the chain, our limits of integration would be from 0 to 20. Our force would be that 0.08 dy, and then the distance that we're lifting up at any given moment is going to be the 20 minus y. Please calculate that for me. Feel free to share it with me if you have it.
16.
Oh, I didn't-
Just 16?
Yeah, that's what I got.
Oh, yeah. Sorry. I was looking at the wrong one. It's like 16 foot-pounds.
16 in pounds, but then the exact same.
Hello. You write 16 in pounds the same.
Yeah,
16
it looks the same
It does.
with money.
Okay.
Pound foot pounds.
Okay, now let's talk about the water. The water we are also
0.08
Yeah, that's exactly what I
an order of magnitude.
yes.
Is water gonna be
It will not. So if we had a bucket that had, was it 16 pounds was the gallon, right? If we had 16 pounds of water, then we could take 16 times 20. But the water is leaking out, right? To where when we get to the top, we have 0 pounds of water. Okay? So what we can think of doing with our water is the same thing that we did with our rope, right? By the time we get the rope all the way in, it weighs 0 pounds. By the time we get the water all the way up, it weighs 0 pounds.
So what is this? 16 minus
Well, we can think of the water weighing 16 pounds per 20 feet, right? Because we have that proportion of it's going to be 0 when we get to the top.
of 20 minus.
Of 20 minus y again, because we're lifting it all the way. Yes.
That's fine.
Would that be the same as if you did? What is it? Yeah, if you did the integral from 0 to 16 as 16 minus
Why 16?
because like instead of taking it in terms of the height, you take it in terms of how many gallons you had because it has to go from.
Well, no, because we're talking about lifting an object vertically, so our y is representing distance.
Yeah.
So we always need to be integrating with respect to that distance.
Okay.
Yeah.
Yeah.
Okay, so total, okay, 100 plus 160 plus 16, we're talking about 276 foot-pounds.
What was the question?
Fiddle.
The work to lift everything up. Because you're doing it all at once. You have 3 separate pieces, but it's happening all at once. Okay?
Well, if I ever end up in such a situation,
You'll know. Hey, you never know. Has anyone ever watched the show Scorpion? No one?
I've seen a lot of.
They're like the geniuses who like go and like save the world. I love numbers.
Can we watch numbers in here?
No, we're not
We should do that on our own.
Okay,
What's the cone?
this is a problem. Really, I can promise you that there will be a chain problem on your quiz. I can promise you there will be one of these problems on your quiz.
What's the cone of this thing?
A water tank in the shape of a cone, radius 2 feet and height of 8 feet, is full of water. I want to know the work to pump all of the water to a height of 5 feet above the tank. Okay? Engineers, very practical problem for you. Right? There's water in a tank. And then we're pumping it up 5 feet above.
So it's kind of like a fountain.
Oh,
I was thinking of something like where's the water going?
yeah.
It's just gonna spray
Stay
everywhere.
right there.
Well, it depends on what we're doing.
The APE test until this could be problem.
What's the shape of the cone?
Assume the spherical cap.
What?
Physics.
A spherical cow?
Yeah, in physics you just assume things are spheres to make it easier to calculate stuff like that.
A cow?
Yeah, like I think of one problem was like assume a horse is a sphere. Wasn't that on an actual test?
I don't remember. I don't
think
I
there
don't
was
even
one where it
remember
was
how
just
that came
like-
Does
about.
everyone have the information that they would like?
Yes.
Okay, I don't hear a no. Okay, you're good. All right. So something that you need to know is that the density of water. What does density mean?
How much stuff there is per amount. How packed it is.
Beautiful. Oh, but it's in pounds. Oh no.
The density of water is 62.4 pounds per cubic foot.
Ew.
Thank you for your amazing description. Okay. And we are talking about a cone full of water, radius of 2, height of 8, and we're pumping water all the way to 5 feet above. So this distance right here is 5. And the water, I don't know what's happening, but that's where it's
Who's
going.
drinking it?
We will be doing a lab, and I'm actually like really sad. Somehow, like our in-service day is on a Monday instead of a Friday. We will do a lab where we will calculate the work of us drinking water from a cup. Okay? Get ready.
Get ready to rumble.
Yes. That is it. Okay? So, hey, guys, focus. All right. So when we set up our integral, we need to imagine discs of water that we are like lifting up, okay? Why do I say that? Well, a disc of water here is going to be different than a disc of water here, right? That's our varying force. So let's think about how do we find the area of a circle? Pi r squared, okay? And then
Oh, we're gonna multiply by the minute.
just I just really need you to, okay? The radius. It would be changing. So let's think of this line right here. It has a slope of up 8 over 2. So y equals 4x. Or x equals y over 4. We're talking about vertical, so it needs to be in terms of y. Okay? So each disc of water is going to weigh pi r squared H times the density. So each circle of water is pi r squared times its thickness, dy, times the density. Now, how far is it traveling up? 5 feet above. So how far total? So 13 minus y is what would go in our integral as our displacement. However, where do we have water? We have water from like 0 to 8. So our limits of integration would be 0 to 8.
Okay.
Would we be given the density?
Yeah, I'll need to do it. I can do that for you. Typically it's going to be water, but okay. Thoughts, questions, concerns? Isn't that cool? Now, if you had like a square tank, you wouldn't have to worry too much because your water isn't like changing, right? Or if you had a cylindrical tank, that would make it less complicated as well. Your circles of water would be the same. You wouldn't have to write it in terms of y. But since we have a cone, our circles of water that we're pumping up are changing, and so we have to write the weight of those discs of water in terms of a variable because they are forever changing.
So it's not like pumping at a constant rate.
No
Because
way.
if you had a certain volume of water, regardless of what shape it was in, shouldn't it take the same amount of work?
Assuming
No.
the tube that is sucking the water out of the
I
pump
don't
is moving
know.
at a non-constant rate.
Yes.
Because,
So the answer
like,
is,
think about drinking water. Like, when it's full, it takes a lot more effort to drink it than when you have, like, just the stuff at the bottom, right? It's because we're having to, like, pump all of that up. Do you understand what I'm saying?
Yeah.
Oh, so you're drinking the bottom of the cup first. So it takes
My
more
God,
effort.
yeah.
Well, but it's kind of like you're taking from the top first. Like, the top has to, like, work its way down.
Yeah.
You got the answer?
you're wondering if-
Oh, we can write it in a decimal.
23,296.
You can write it as a decimal.
I just wanted to see what the fraction was. Because the answer of the integral is a clean fraction.